Hi, everyone. We're going to go ahead and kind of get started. Before I introduce today's speaker, we'd first like to acknowledge the Materials Decarbonization and Sustainability Center. The industry affiliates that are backing the center are visionary leaders who are helping our center maximize reach and efficacy. We're really grateful to all of these organizations involved, and we always welcome more members if anyone else is interested in joining. More information about the center can be found at our website, which is shown at the bottom of the screen here. Now, I have the privilege of introducing our speaker today, Dr. Seth Kane. Seth completed his PhD at Montana State University, and he's currently doing his postdoctoral studies here at UC Davis. His PhD is in mechanical engineering with an emphasis in material science, and his postdoctoral work is focusing in on industrial ecology methods. His overall research emphasizes sustainable materials development and carbon sequestration methods, particularly within the built environment and through utilization of carbon within novel materials. His work encompasses materials, including polymers, cementitious materials, biomass, carbon, and composite materials, as well as novel technologies, including applications of pyrolysis, additive manufacturing, alternative recycling, and energy storage. Today, he is going to focus in on pathways that utilize locally available biomass residues in materials production. Thank you, Seth, for presenting today, and we look forward to your talk. You could take it away.
Awesome. Thank you, Savvy, for the introduction, and thanks everybody for being here today. So as Savvy mentioned, I'm going to be talking about pathways that we can take to utilize different biomass residues in different materials, how those can contribute to decarbonization of materials production, and how those can contribute to carbon dioxide removal broadly. Okay, and so we're going to try to go through three goals of how to use these materials. The first is to talk about what pathways have been examined that allow us to utilize these biomass residues in materials production. The second is going to be what trade-offs are there between using those biomass residues for energy producing processes versus using them in materials, and what considerations we might want to make between different pathways to utilize those in the best way possible. And then how we can utilize those residues in which materials. So are there particular residues that work well in one material, but not another? And so to start with, I want to talk a little bit, give some context around what global materials production looks like and what the availability of biomass residues look like in comparison to that. And so when we look at the materials that we're producing, there's a lot of cement, a lot of wood, a lot of asphalt, some brick, steel, ceramics, and plastics. Of that concrete, about 4.2 gigatons is cement. And relative to that, we are producing more agricultural residues than any individual chemically processed material. So not including the aggregate in that concrete, there's more total agricultural residues than any individual material. In addition, there's some forestry residues. And when we're talking about this masses, and we're going to carry this through, this is the amount of these residues that we can collect under sustainable agricultural practices. So leaving enough in the fields to allow for the soil to regenerate, not just pulling everything out. When we look at the emissions from this, we can see our iron and steel and plastics move up a bit and become the second and third most emitter, even though they had a little bit less production. And we can compare this against the amount of carbon that is uptaken by photosynthesis and stored in our forestry residues. And between the 7 materials shown here, we emit about the same amount of carbon from production of these materials as are stored in agricultural and forestry residues. So we can see there's really a lot of potential here, both in terms of the amount of mass produced and the carbon fluxes into these materials to potentially use these to offset some of the emissions from materials production and enough mass of these to do this at a fairly large scale. And we're going to focus most of our discussion in on these big three of concrete, steel, and plastics, and really mostly on concrete and plastics for some reasons we'll get into in just a little bit. It's important to note also that when we're talking about these residues, they're not all the same, and we don't produce the same amount of all of them. So we really produce a lot of corn straw, and then after that, rice straw, forest residues, and wheat straw, with some lower amounts of some other residues. In addition, focusing in on those 4 highest produced residues, we can see that they have some variations in properties. So here we're showing the 3 key organic components of biomass. That's going to be your cellulose, your hemicellulose, and your lignin. These make up most of our plant-based biomass globally. And then there's also an inorganic component of we can see that these vary a little bit with our wood-based biomass having more lignin and less hemicellulose, and our straws having more. When we look at the composition of that ash, which is going to be important for using these materials in concrete, we can see that relative to the other materials, the rice straw really has a lot of silica content. That'll give it some pozzolanic reactivity in our concrete. And in contrast, there is very little ash in our wood-based materials, but a higher percentage of that ash is calcium than in those other materials. Okay, so that's what we have for biomass in the context of material production. So how does this fit into how we're thinking about decarbonizing materials production currently, as well as how we're thinking about carbon fluxes as a whole currently? And so this is a figure from the IPCC showing the amount of carbon dioxide removal that we will need to meet net zero by 2100. And that is a fairly significant amount. And one key way we can do this is by storing carbon in the materials that we're already producing. And so this is from an excellent paper from a recent PhD graduate in Professor Miller's group, Dr. Van Roheen, that was recently published in Science, examining different ways that we can store carbon in materials. And I've highlighted in green here the different pathways that could potentially utilize biomass residues. And so those are integrating biochar into cement, wood-based products, and in particular applications like particle board, where we could potentially be using residues, bio-based plastics, biomass fibers and brick, and then no bio-based asphalt. We are mostly going to focus our discussion of this on that biochar and cement, as well as a few other pathways that weren't included in this work. But it is important to note that there's these other pathways as well, and we'll discuss those a little bit as we go through. And so when we look at roadmaps for decarbonizing concrete, this figure is from a paper that was published in Nature about a month ago. There's a number of different ways we can integrate biomass to do this. So here I've highlighted using less clinker. If we're replacing primary clinker with biomass-based products, we're using less clinker. Potentially integrating these materials can increase the porosity of concrete, which might allow for more CO2 capture and storage. And then if we're adding biochar, as we saw in the previous slide, we're potentially creating carbon negative materials that are being added in there. And so these can play a role there. We also in steel is a little bit different, primarily because we're already doing this a little bit, mostly in Brazil. So I've highlighted in green there. This is a figure from the IEA. 2 different ways of accounting for the emissions of Brazil's steel production. The one on the left is if you account for the use of bio-based carbon as entirely negative, and you can see in that case, they have some of the lowest emissions of any country for steel production. And that's because they're using about 10 million tons of bio-based carbon in place of fossil fuel derived coke coal. However, they're not always using residues for that. And when you account for those agricultural emissions, that does go up a bit, which is what's shown in the green bar on the right there. And so this already exists at a very high technology readiness level, as I said, about 10 million tons per year in Brazil. And there's also some pathways to do this with different technologies, such as torrefication of biomass, which we won't be talking about. And so the reason I'm not focusing on steel as much is that these pathways are a little bit more widely applied relative to some of the others that we'll be discussing. And then finally in plastics, this is again a paper from Dr. Van Roheen looking at different pathways that we can store carbon in plastics. And you can see that a number of these pathways involve biomass residues. So wheat straw, corn stover, sugar bagasse. These are all byproducts from agriculture that we then can use as feedstocks to produce these materials and potentially store carbon in these materials. Okay, so we've discussed a little bit how this fits into existing roadmaps for decarbonizing the materials. And so now I want to discuss a little bit of the exact pathways that we can use to process this biomass and potentially produce materials or energy. And so the first of the pathways we'll be discussing is combustion of that biomass. So this is where we burn the biomass under excess oxygen, a process I'm sure we're all familiar with. And our primary products are going to be an energy product. And then that ash will vary a little bit depending on the ash composition of the original biomass. So as we saw earlier, if it's wood, there might be a little bit less ash. If it's a wheat straw, there might be a little bit more ash. And depending on the exact facility design, this can cause some issues during combustion of the biomass. If it is very high ash, potentially can form some slag products that might be detrimental to running your process. Yeah, the second process we're going to talk about is gasification. So this has then slightly limited oxygen, so not complete combustion. And you're producing energy, a syngas product, which is a mix of carbon monoxide, hydrogen, methane, and carbon dioxide, and then a small amount of a solid biochar product. We're going to be talking about biochar a lot. It is a largely carbon material that is the solid product of these partial and complete pyrolysis processes. So it's taking that biogenic carbon that is unstable, is able to be biodegraded, and converting it into a more stable aromatic carbon form that we can then use as a material. This has been pretty widely applied for carbon dioxide removal and also for agricultural soil amendments, and is currently one of the most widely delivered carbon dioxide removal methods. And then our final method here we have is pyrolysis. That is the typical process that's used to produce biochar. And it will produce, in addition, about 30% of the weight of the original biomass as syngas, about 25 to 45% biochar, depending on that content present in the biomass to start with. So that ash is going to end up in the biochar along with that carbon product. And then in addition, a bio oil, which is a mix of lower molecular weight carbon products that are in the liquid form. You can run this process at different heating rates. So at very high heating rates, you'll have a fast pyrolysis process, which will produce more bio oil. At slower heating rates, you'll have a slow pyrolysis process that will produce more biochar. But functionally, these materials are fairly similar. Can still be modified to have the properties that we need to use them in materials. And so we're a little bit going to be discussing gasification and pyrolysis together as processes that produce biochar. Just keep in mind that the relative amount of biochar we might be producing will be different between those processes. And when we look at these trade-offs, we can see that typically our combustion process is producing more energy, but less materials with almost no biomass carbon present. And then as we move to the right here, we're producing less energy and more materials, with these ranges showing the different variations between different biomass types. In addition, from that pyrolysis process, we can use that bio oil product as either a fuel source, so combusting it, or as a material, potentially in bio-based asphalt, as we saw in one of the earlier slides. And that just has a little bit of a trade-off depending on, is there a market for that bio-based asphalt, or is it easier just to burn it? But we can then store more carbon potentially by utilizing that. In addition to those thermal conversion pathways, we can use some of these biomass residues directly. So that might be, for example, in a composite material. One that a lot of people are familiar with might be Trex decking, which utilizes sawdust in a polymer composite. But there's also things like hempcrete. You can potentially use some of these biomass residues in place of primary wood in particle board and plywood, and that's been done by a number of startups. Straw bale insulation is an example of using these biomass residues as an insulation material, or you can chemically convert them, be that either to like bioplastics or in a biorefinery to separate out, say, the cellulose component of that, and use that in more valuable products. We're mostly going to be focusing on those thermal conversion products and a little bit less on these, but keep in mind that there are ways to use these directly as well. And when we look at all of this together, basically what we see is that there's a linear relationship between the amount of carbon in the material that we're burning for energy and the amount of carbon in the material that we're putting into a material. And as we move into the pathways further to the right here, we reach a point where there's more carbon being stored in the material from that biomass than is being emitted. Okay, so I'm going to start by talking about the combustion product of ash, different ways that we can use that. This is going to be a pathway that prioritizes energy production. So we don't necessarily expect huge benefits from the material itself. It's sort of just a byproduct of that energy generation. And typically from that, we're getting about 1 to 15 weight% of that original biomass input. And this contains very little carbon because it's mostly those inorganic compounds that are present in the biomass. So we're seeing about a negligible amount to about a half a kilogram or 0.05 kilograms of CO2 per kilogram of biomass. You, however, can increase that slightly by carbonating the inorganic compounds present. So for example, calcium oxide to calcium carbonate and store a little bit more CO2 in that material. And so this example here is from a paper by a PhD student that recently graduated from the group, Patrick Cunningham, where he treated different biomass ashes with CO2. It was able to increase that from that maximum of 0.046 we see of just CO2 present in the ashes to about minus 0.1 kilogram of stored CO2. This is still not quite up to the theoretical maximum, but that's dependent a little bit on exact process design and optimization, things like that. Okay, so we then can take this ash and put it in concrete as a supplementary cementitious material, replacing that primary cement fraction of our concrete with either 5 or 15% of these ashes. And here we're just looking at a mortar control compared against a wheat straw ash and a rice hull ash at 5 or 15%. And those are being applied either with or without that CO2 treatment. And so we can see that in general, the rice hull ash is performing a little bit better than that wheat straw ash. That's a result of that higher silica content that we discussed earlier, and that can contribute to those pozzolanic reactions in there. In general, when we are CO2 treating this, that strength is going down. In the case of wheat straw, it's potentially going down a lot. And that's because we're having that CO2 react with some of these compounds that might be participating in the reactions and making those a little bit less reactive. When we look at the greenhouse gas emissions on the right, we can see that all of these processes reduce the total greenhouse gas emissions of that production by about the same amount. There's not a big difference between CO2 treated and untreated, and there's not a big difference between the different ashes. This is because the carbon contained in those is fairly small relative to the offsetting of the emissions of the cement production itself. And so that emissions reduction is mostly dominated by how much of that ash we are putting in rather than the carbon stored in the ash itself. We can do something similar by putting that biomass ash into plastic. So again, we've got a measure of mechanical properties on the left and our global warming potential on the right. And we're using, in this case, 5 and 20%. Again, both that wheat straw and that rice hull ash. And so we can see that we're going to increase the modulus of those plastics, so get a stiffer plastic out as a result of the inclusion of this ash. We would expect a little bit less of a chemical component to this. It's mostly just a filler in these materials, and that filler is not deforming as much as our plastic. So it makes sense that it would get a little bit stiffer. And then we also see about a 5% and 20% reduction in the global warming potential of that plastic as a result of replacing primary plastic with these waste ashes that might have relatively little greenhouse gas emissions associated with them. In this case, we are just showing the CO2 treated ashes in the plastic because there is not that actual chemical interaction. We see basically identical performance mechanically between the treated and untreated with CO2 ashes. And so you can squeeze out a little bit extra benefit here by treating those ashes with carbon dioxide, whereas in the concrete, we do see that reduction in mechanical performance. Okay, so that's kind of two pathways to utilize that biomass ash from combustion. We have a lot of that available already. There's about 1,000 facilities for biomass production globally. And so that's something that we can readily apply with facilities that exist and could be done very quickly. These next two technologies, gasification and pyrolysis, are at much smaller scale. And that's kind of important to keep in mind as we go through. We'll discuss that a little bit at the end. But essentially how these processes work is we'll start with our biomass residues after we've grown the biomass. Because there are not so many of these facilities, typically they might have to be transported then from where the biomass is grown to a gasification or pyrolysis facility where they'll be dried, go through this thermal conversion process, and then you end up with syngas, bio-oil, and biochar. That chemical conversion process or thermal conversion process does require some heat, and the drying does require some heat. Typically, in an efficient and well-designed process, we'll be able to use a small amount of the heat produced from combusting the syngas component to meet the energy demands of that process. However, this does depend a little bit on our exact process design. And then from combustion of that syngas, we get some usable heat as well as some electricity. We can either combust or use our bio-oil as mentioned earlier, and then we get our biochar, which will be mostly what we'll be discussing here. And then again, just to highlight, from our slow pyrolysis, we get a kind of balanced yield of those three products. From our gasification, we're getting a lot of syngas, just a little bit of biochar. And so quantifying the results of this a little bit, we're going to get different amounts of bound carbon out of our pyrolysis process, depending on the exact temperature. This is specific here to pyrolysis, but there would be a similar relationship with lower numbers from gasification. And we can see that as that material thermally degrades, we see a quick decrease in the amount of bound carbon in the biochar at about between 300 and 400 degrees Celsius. This exact amount at lower temperatures is a little bit misleading in this because this is just at the factory gate. It doesn't account for degradation of that material over time. And we'd expect those lower temperature materials to degrade more quickly, whereas the higher temperature materials are quite stable over centuries. We also produce a little bit more energy as we increase that process temperature. This is a result of the hydrogen groups present in that biomass reacting off, and we're then able to use that hydrogen for energy, and our CO2 emissions stay pretty stable along with that bound carbon as we increase our temperature. In addition, it's worth thinking about that these processes can be designed in different ways. So we could have a highly efficient process where we're reusing that heat from combusting the syngas to meet our energy needs. We're using a combined heat and power process to capture the most energy we can from those products we are combusting. We have high thermal efficiency, and we're using that bio-oil for material production. Or we could have a very inefficient kind of poor practices scenario where we're using a fossil fuel input to meet our energy needs, or we're just flaring our energy products, and we're running this process with fairly low thermal efficiency. And those will have fairly different outcomes. And so these figures are showing an uncertainty assessment of those two scenarios. And just to give an idea, even with fairly high uncertainty considered, that inefficient poor practices scenario across basically the entire distribution, we would have to be putting energy in, whereas in an efficient scenario, we get energy out across the entire distribution. And similarly, for the net emissions, we are storing carbon across basically the entire distribution for an efficient scenario, whereas it's very uncertain whether we emit or store carbon in that inefficient scenario. So exactly how we do this matters. About a quarter of current biochar producers report not using their energy products for anything, just flaring them. And so this poor practices scenario is not that unrealistic for current production. And it's important to keep in mind that how we make the biochar matters, not just what we do with it. Okay, so in steel production, as mentioned, we do use about 10 million tons a year of bio-based coke, mostly in Brazil, but that's not all from residues. This can get used across the steel production process. So we have different carbon inputs of either coal or coke in the sintering and pelletizing process. We have coal inputs to the coke making process that can potentially be replaced with biomass-based carbon. And then we have coke inputs to the blast furnace. The key characteristics performance in this are going to be that for coke in the blast furnace itself, you need fairly high mechanical strength to support the iron ore on top of that coke, because you flow the air up through the coke to produce the reducing gas. You need fairly low ash content, and particularly silica. If you have additional silica, you then need to add additional lime into your process to form slag from that. And that's going to be associated with additional greenhouse gas emissions. Higher heating value is going to be more beneficial. All of these are going to be a little bit lower than fossil-based coke for their higher heating value, but the closer we can get, the better. And then you want to have very low decomposition at low temperatures, so you can really allow that process to get up to the high temperatures that we need for steel making without having any degradation. And as mentioned, we're not going to talk about steel making a ton, just because this is more of an energy application almost in material production rather than a material pathway itself. And because it is being combusted, we're not necessarily storing any carbon, which is really what we want to focus on. So then after that, moving on to using biochar in concrete. This is from a paper out of Colorado School of Mines and National Renewable Energy Lab, who did a really great job of systematically looking at what are the effects of biochar in concrete. How can we modify the properties of biochar to maximize that performance in concrete? And the three key outcomes they found were that biochar will absorb some moisture from your concrete mixture, and that's going to decrease the effective water to binder ratio in that mixture. We know as that water to binder ratio decreases, our strength will increase, but it gets harder to work with. And so we really want to find a balance, integrate this into our concrete mixture design so that we can maximize those properties and get as close as we need to our designed properties. In addition, the silicon content in the biochar will contribute to pozzolanic reactions. This is very similar to some of our other common supplementary cementitious materials that are high in silica and promote the formation of calcium silica hydrate rather than calcium hydrate, which we know increases the strength in our biochar or in our concrete from a result of that silicon in our biochar. And then finally, different surface functionalizations in the biochar can increase the hydrophobicity of that biochar, which might decrease the interfacial strength between it and our cementitious matrix. This can be represented pretty well by the oxygen content of the biochar, and reducing that can improve the strength overall of our concrete with biochar. And so these are the three properties that came out of that exact model, but we also can make some inferences about what might be the best feedstock by thinking about what we want in supplementary cementitious materials pretty broadly. So if we think about our different inorganic compounds, our calcium, and specifically our calcium to silica ratio in our SCMs, our alumina content of our SCMs, different alkali and alkaline compounds that might be participating in those cementitious reactions in potentially a detrimental way, our sulfur content. And then finally, I've left this to the end because we can tune it a little bit, but it does require some energy inputs to do so. The particle size of our biochar should be pretty similar or a little bit smaller than the particle size of our cement particles to make sure that that's well distributed throughout the material. And so now thinking about the outcomes, this is leveraging a predictive model for biochar properties that we developed in our group, specifically for thinking about biochar life cycle inventories, as well as that strength model developed by the folks at Colorado School of Mines and NREL. And they're looking at 10% clinker replacement reporting strength here for a mortar that is about 44 megapascal strength with no biochar added. You'll remember here that our rice straw was our high silica content biomass, and we can see that that results in the largest increase in strength. When we think about greenhouse gas emissions, we can see that the highest reduction in greenhouse gas emissions, so this is both the carbon stored in the biochar and the reduction in emissions from using cement, with some of those processing emissions then subtracted out, results from our high temperature biochars, and specifically our high temperature biochars that are highest in carbon. So because our poplar-based biochars had low ash content to start with, they had higher carbon in the material to start with, and more of that can be stored in the material, resulting in the greatest reduction in strength. In addition, even though the poplar does not have it has little, if any, silica content. It does have very little oxygen, and it does uptake a little bit less water than those other biochars. And so it has quite good strength performance as well. It's important to think about the durability of these materials. So here I'm showing a plot of the carbon permanent. So this is the percentage of the CO2 in the biochar that will be reacted off after 100 years if it was in soil. There's not great data for biochar carbon permanence in concrete. And so we've been using soil as kind of a worst case scenario. We know it probably will not be this bad, but it does represent a good kind of upper limit, worst case. This is how much carbon could be degrading. And again, we can see that 300 degrees Celsius biochar, we're losing a lot of the carbon over time, whereas at those higher temperatures, we're only losing a couple of percent. We would expect that as that carbon degrades, there's potentially going to be some additional voids in the concrete as a result of that. And so this might contribute negatively to the durability in addition to that loss of stored carbon in the material. In addition, we know that the introduction of that biochar will slightly increase the porosity of our carbon or of our concrete as a result of the porosity of the carbon in the biochar. But it also then has the competing effect of those pozzolanic reactions as a result of the silica do reduce the porosity. So we have these two competing effects in terms of porosity that's going to affect things like carbonation, chloride resistance, things like that. And then it will also impact the durability. So as mentioned, that water to binder ratio is heavily modified by biochar absorbing water. In addition, it can have some interactions or absorption of admixtures such as superplasticizers that might be added in there. And so designing your entire concrete mix around the biochar rather than just adding it in is going to be important for getting good workability properties. Durability is really an area where there's a pretty big need for additional research in this space and long-term testing to kind of validate what we would expect from the performance of these materials. So to put this in context of concrete and cement production and how much biochar we might be able to use, we currently produce about 4,200 million tons of cement, about 340 million tons of fly ash, which is one of our common SCMs that we're using today, about 350 million tons of blast furnace slag, again, a common SCM that we're using today. So those are all pretty large numbers. In contrast, we're only producing about 0.35 million tons of biochar currently. So obviously that cannot be a drop-in replacement right now at this moment for that existing SCMs. However, this industry has been growing quite quickly. It's been more than doubling the amount of biochar produced annually the last couple of years. And those total residues that are available, we could produce up to 1,200 million tons, which would be much more than we could use in that cement production at that 10% replacement. So there is a lot of potential. We don't necessarily have to stretch our available biomass residues very thin to be meeting, say, a 10% replacement of cement production with biochar. And that's not accounting for that we might be using other SCMs. We don't expect to have that much less slag. All kind of trade-offs in how we go about decarbonizing this, how much carbon we are able to store in these materials. Okay, so finally, we've got our biochar and our plastics. So this data is again showing a mechanical indicator of tensile failure strength on the left, and then some greenhouse gas emission data on the right. Looking at introducing 20 or 40% of a commercially available wood-derived biochar into high-density polyethylene on the left, and then a couple of biodegradable plastics, recycled high-density polyethylene, and primary high-density polyethylene on the right. And so we can see that in that recycled high-density polyethylene, we see an increase in strength with the introduction of biochar. This is a result of mechanical interlocking between the porous structure of the biochar, as well as some strengthening mechanisms that are similar to what we see in carbon-derived additives for plastics, such as carbon black. And we see a pretty big reduction in the overall global warming potential of that plastics production as a result of introducing that biochar. Because there is so much carbon stored in this biochar, unlike in the biomass ashes, we're seeing a reduction, whereas in the biomass ashes, we were seeing a reduction of about the amount that we were adding. Here we're seeing a reduction of about double the amount that we're adding. And that's because of that carbon stored in the biochar. As a result of this, at 40% addition in our recycled HDPE, we can get to negative emissions, and we see greatly reduced emissions, 40% addition in the other plastics as well. This does depend a little bit on exactly what biochar you use and what plastic you're putting it in. So biochar can have some negative interactions in some plastics. So here, this is no longer an agricultural residue, but it is a waste product of a food waste derived biochar. being added into high density polyethylene and our biodegradable polylactic acid. And we can see that that higher inorganic content from our food waste and our biochar gives us a little bit less of a benefit than we were seeing with that wood-derived biochar, particularly in PLA, where we begin to see a decrease in strength above about 5% addition, whereas in that HDPE, we see an increase in strength across the entire range of additions. However, there are then some interesting interactions. For example, if we wanted to have our PLA biodegrade at the end of life, the addition of that biochar does decrease the composting time of that PLA, which in some scenarios might be beneficial. And that's a result of it allowing more moisture to travel into the structure of the PLA and allow that hydrolytic degradation to occur a little bit quicker. So there's potential ways that we can integrate this into different plastics for different applications. Exactly how we do that will depend on the exact application of those plastics, which might be a little bit more varied than our application of our concrete, as well as the higher variation in properties between our different plastic types. Yeah, when we think about what we want, whereas in our concrete, we wanted high silica content and hydrophilic biochars, here in our plastics, we want low ash content, high carbon content, hydrophobic biochars. So we're not necessarily seeing the exact same resources being the most beneficial in each of these cases. So we might want some more wood-derived high temperature biochars in our plastics, whereas we might want something like rice hull ash in our concrete. Thinking about the availability of these, there's only about 400 million tons of plastic production globally. We can't apply our biochar in all applications. And so we could potentially be replacing some of our petroleum-derived carbon additives in a number of applications with biochar quite easily. And it's been pretty well demonstrated that these have equivalent properties. So going through the couple of things that we discussed here, what pathways have been examined to utilize biomass residues in materials production? So we've looked at direct use of those biomass briefly, use of combustion ashes, and then use of biochar produced from gasification and pyrolysis. For ashes, just plastic and concrete production, and for our biochar in all three of steel, plastic, and concrete production. For the trade-offs, we know that in our more oxygen present thermal conversion processes, we're going to be producing more bio-based energy, but less materials. And those materials might contain a lot less carbon because we've converted that to CO2 during producing energy, whereas our pyrolysis and gasification processes result in a higher carbon material that can potentially have greater benefits in materials production, but we're producing a lot less energy as a result of that carbon being stored. And so a trade-off there that's going to depend on exactly what the emissions of your materials production and energy locally look like. And then finally, we've got which biomass residues can best be applied in which materials. So we see wood-based residues potentially being more beneficial in our plastic applications, rice hull ash and high silica content biomass being more beneficial in our concrete application, and overall looking to maximize our carbon content that we're putting into those materials if our goal is to store carbon in those materials. And so just briefly, as we wrap up, a little bit of discussion around the actual application of this. All of the applications we've discussed today have been applied commercially at least at pilot scale and are rapidly growing. So there's a lot of interest in this currently across all of these applications. One thing that is really needed on the concrete side is standards for the use of biomass residues as an SCM. So getting some standardization around different practices for this, and then communicating that out to practitioners so that these can be applied. From the biochar suppliers, there's a need for increased biochar availability, as we saw that amount of biochar produced is relatively low relative to the materials production, as well as consistency in the product produced over time and design of that process to be specific to material science applications rather than agricultural applications. So on the consistency side, you want to make sure if you're designing your concrete batching plant around potentially integrating biochar, that you know you're getting the same biochar product batch over batch. You're not going to get something that all of a sudden absorbs way more water than your previous batch, things like that. And then leaning towards higher temperature production for better performance in materials, whereas some of the agricultural applications that are being commercialized currently trend towards lower temperature production of that biochar. And then on the economic side, biochar is currently $235 per dry ton at the factory gate if you're purchasing a high volume. That is a little bit higher than the current price of cement, much higher than some of the existing SCMs. But if we're looking on the plastic side, that's much lower than the price of current commodity plastics. However, there also is some scenarios where the carbon credits associated with that biochar have already been sold. And we see a big increase in the purchasing of biochar for carbon credits currently. And in that case, biochar, we're hearing from producers, is sometimes available at quite low prices. You wouldn't quite be getting the full benefits of that carbon storage because those have already been used to offset other emissions, but potentially could still get some of the benefits in material properties and material production emissions from using that, and potentially at a low cost. As I wrap up, I'd like to thank all of the members of Professor Sabby Miller's lab group that have contributed to this work. That's going to be Dr. Jin Fan, a postdoc in the group, Dr. Petra Cunningham, and Elizabeth Van Roheen, recent PhD student graduates in the group, Josephine Olson, a current PhD student in the group. And then I'd like to thank our collaborators at Montana State University that contributed heavily to both the biochar in plastics and the biomass ash in plastics. That's going to be Professor Cecily Ryan and Babatunde Olonge, who's a PhD student in Dr. Ryan's group, as well as our collaborators at UC Berkeley and Lawrence Berkeley Lab, and Professor Arpad Horvath and Dr. Corinne Scown's groups. With that, I'm happy to take any questions.
Awesome. Thanks so much, Seth. I realize that in a webinar setting, you don't get the applause, but imagine loud applause. And as we wait for folks to start to enter questions, please do plop your questions in the Q&A and we will start to address them one by one. As we're waiting for folks to plop some more questions in, I thought I would ask kind of as a kickoff question, do you consider these biomass solutions that you kind of have gone over as more regional solutions, or are they ones that can actually be implemented globally? Do you see any issues kind of coming up from transporting these resources? Does that undermine emission savings, et cetera? Any thoughts on that?
Yeah, so we know that different biomass residues are produced in different parts of the world, and cement production especially is quite globalized. And so there are some regions where you might not be able to use the optimal performing biochar in your material. However, the differences between, say, the rice straw ash and corn straw, as an example, are going to be smaller than the resulting emissions from transportation. And so in those cases, it might be better to use a locally available residue rather than shipping your rice hull ash across the world. In the case of plastics, we do know that it's much more localized production than concrete. However, you also need a smaller amount of total material if you were to replace a high fraction of plastic with biochar. And with forestry residues being fairly global in their production, it's likely that shipping concerns will play a smaller role there.
Awesome, thanks. I see we have a question in our Q&A box that I will read to you, but in case you want to see it visually, it's in there as well. Are there any specific cases in which dedicated crops outperform biomass residues in terms of overall carbon sequestration?
I think not for carbon. If your focus is carbon sequestration, because you're going to have those fertilizer inputs that have embodied carbon associated with them, because you're going to have land use changes, those often will offset some of the benefits of things like specific energy crops, maybe for this application. If your focus is carbon sequestration, you could optimize your process for other things. So for example, for material performance, it might be better to be specifically growing a product where you know you're going to get something consistent. And that comes up a lot in some of the more material science focus aspects of applying these bio-based carbons, such as carbon materials for batteries, where you might want very specific properties that might be hard to get with residues.
Awesome. I realized it was a bit outside the scope of your talk, so this is more of a thinking exercise, and I realize you might not have an answer, but do you have a sense as to whether or not the inclusion of these residues or these co-products effectively of energy generation, do those affect the recyclability of any of the materials that they then get used in, or the end of life management of any of those materials?
Mm-hmm. Yeah, so with plastics, it definitely would. We see this with conventional carbon additives as well, that if you're introducing large amounts of those, it gets much harder to process with our current mechanical recycling techniques. Um, in concrete, I don't think that there's been any studies done on using concrete with biochar as aggregate, um, but I think we would expect that to perform pretty similarly to some of those other SCMs. And then in steel, where it's just being used as sort of that energy source and carbon for reduction, I don't think we would expect almost any changes, probably no changes in the material composition as a result of using that. And so it would be just as recyclable as otherwise.
And if I misread any of the questions, please do jump in and feel free to correct and or add on to any of the questions that were asked. I'm curious in terms of how one considers the storage capability, the carbon storage capability of these resources. How do the dynamic factors of how quickly the carbon dioxide is removed from the atmosphere during plant growth versus emissions in order to do any of these processes, versus the storage capability, how does that start to play a role in terms of the ability to actually use this as a carbon sink, for lack of a better term? Is it really actually creating a meaningful storage mechanism, or is it more delaying the emissions associated with these materials and resources?
Yeah, so in the case of the agricultural residues, where we're growing those every year, harvesting them every year, in some cases potentially multiple times a year, um, that really is going to be acting as a fairly immediate carbon sink for something that might otherwise be burned or biodegrade, um, and release that carbon back into the atmosphere. For the forestry residues, that has been stored over decades, but we are emitting the carbon from those forestry residues that are not currently being utilized every year. Um, as we are harvesting that amount of wood resulting in those residues each year. And so it has been previously stored, but would be re-entering the carbon cycle at kind of a steady rate from those materials. Um, and that's something important to consider with the low temperature biochars as well. They do degrade and lose a large fraction of that carbon over time if you're producing biochar at 300 degrees Celsius. But that's still storing that carbon for potentially 50, 60, 70 years into the future. Prior to that degradation, it's still storing a portion of that carbon, essentially on a century level scale. Um, yeah. Another consideration with the plastics end of life from earlier is if those plastics are incinerated, which is currently a um, end of life pathway for a decent chunk of our plastics, that carbon then will be emitted back to the air. Plastics essentially have a shorter material lifespan than something like concrete. Um, and so in the case that it is used and then incinerated, we might not be storing that carbon for very long at all. But at least we would be capturing that energy in the biochar carbon during that incineration process, hopefully.
That makes sense. How does the use of these resources alter the aesthetics of the materials?
So starting with plastics, you basically will only be able to make black plastic from biochar. And that's similar to using some of our carbon-based carbon black pigments and things like that in our plastics. The carbon structure between those materials is quite similar. The performance is quite similar. And as a result, you get a black color. Um, for concrete, it's going to be darker. It's not quite black, but there might be some applications where that's undesirable. Um, and I believe there's been some studies in both of those materials. One of the commercial companies producing biochar plastic composites is doing so as exterior building siding, and then also in biochar and concrete for buildings. If you are making that building a darker color, you're potentially absorbing more energy from sunlight, which might then result in increased HVAC costs as a result. But a little bit of a trade-off there, and I think the sort of thing that maybe can be accounted for at other points in the design process, but does need to be accounted for.
Awesome. Do existing policies and carbon markets provide incentives for the use of these resources? Are they currently reliant on those? Is there a viable business case for these materials without those incentives?
Yeah, so as mentioned, biochar is the largest delivered CDR credit mechanism currently. And I think that the CDR market has kind of been responding to that. We see an increase in sales of biochar-based CDR relative to other mechanisms of CDR. I'm not super familiar with what the situation would look like without those carbon markets in place. Other than that, we do see the fastest growth in areas where there are robust carbon markets, which might indicate without them, it's a little bit financially challenging.
That makes sense. Are there limitations or competing uses for the residues that could affect large-scale adoption?
Yeah, so that's definitely, I think one of the things we want to highlight is a lot of these are being used for combustion currently. Some of them are being left in the soil, some of them are being composted. All of these different pathways that we utilize these currently. And the goal is hopefully to move towards pathways that are optimized from a climate perspective, are optimized from a performance perspective. If you are currently combusting your residues, maybe you might be more interested in producing a smaller amount of energy and a larger amount of material. Having people think about those trade-offs in this decision making, and hopefully having additional markets develop for these materials, and see more of them be utilized rather than biodegrading or being combusted without energy recovery, would really be the goal.
Do you have a sense of how forest thinning could play a role in biomass resource availability for other products?
Yeah, so there's definitely things like wildfire prevention, where we might have some forest thinning taking place. The materials produced from that might not be super viable to use for, say, existing lumber mill operations, and potentially have a lot of application in biochar. We actually see a lot of production of biochar being done by the US Forest Service. They've designed a specific kiln for it that they can haul into the forest, to then, rather than having these big slash piles, produce biochar, store that in the soil in the forests, where potentially they could be hauling that biochar out. In some cases, that might not be super feasible just because of the remoteness of those locations, but then using it for materials applications rather than leaving it in the forest.
Awesome. I'm not seeing other questions popping up in the chat or the Q&A. Have I missed anybody's? Hopefully not. All right. In which case, thank you again so much, Seth. Really enjoyed this talk, and we will be posting it shortly. So thank you all for attending, and thank you again, Seth, for this talk.
Yeah, thank you everyone for coming.